So the differential equation we're thinking about here is dy dt equals f of ty equals t plus y. Well, let's pick a particular initial condition, say y of 0 equals 1. Let's think about it geometrically. That's probably the best thing to do in a short amount of time. We want to think about approximating the solution of that differential equation's initial value problem going through this point, 0, 1. Y equals 0 when t equals 1. The solution has to follow the slope field. What is the slope of the little line segment in the slope field at this point? You got to plug that point into the right-hand side. F of 0, 1 is 0 plus 1 is 1. The slope mark in the slope field is going to have a slope of 1 right there. That's going to be tangent to the solution curve that passes through that point. Tangent lines approximate curves, nice curves at least. Why not use the tangent line to approximate the solution? At least for a short amount of time. Maybe out to t equals 0.1. The slope of this is 1. If I go out to t equals 0.1 with a slope of 1, the coordinates of this point are going to be 0.1 comma 1.1, right? Because I increased t by 0.1 and the slope is 1, so y's got to increase by 0.1. Well, maybe I should use that point to put it into the slope field and find the next slope. What's f of 0.1 comma 1.1? It's 0.1 plus 1.1 is 1.2. The solution curve that goes through that point has a slope of 1.2. Slope equals 1.2. Now realize we made an error here in approximating the true solution. The true solution probably is doing something like this. And this point is not even on the graph of the true solution. So by using this next little line segment, and it's the slope there to approximate the solution over the next interval from 0.1 to 0.2, we've already missed the solution. We're already off of it. But hey, life's imperfect. Do it anyway. What are the coordinates of this point going to be? 0.2 comma something. The slope is 1.2. If t increases by 0.1, y has got to increase by 1.2 times 0.1. 0.12, I guess, to 1.22. I did that in my head correctly. From 1.1 up by 1/10 of this, 0.12, that'll bring me to 1.22. Then do the same thing. Find the slope of the slope field here, follow it forward for 0.1 units of time. What's the slope right there? It'd be f of 0.2 comma 1.22. 0.2 plus 1.22. I'm using the formula here for this function. And that's 1.42. Slope equals 1.42. The next point would be 0.3 comma 1.22 plus 1/10 of this. 1.22 plus 0.1 times 1.42. It's 1.22 plus 0.142 is 1.362. Is that right? 1.362. That's the idea of Euler's method geometrically. As you might expect, our textbook doesn't derive it geometrically. They derive it with Taylor's theorem. But you can think about it geometrically too. Thinking about it with Taylor's theorem helps you think about errors, as should not be surprising by now. Though when you think about errors in reading section 5.2, it gets pretty nasty. Give it your best shot anyway. See you next Tuesday.